Welcome to this webinar organized by the IEA MSDTC. I'm Steve Fisher. I have the pleasure of chairing the MSDTC for the IEA, and very proud tonight to introduce Dr. Gwanseob Shin as our speaker this evening, or this morning, depending on where you are in the world. Gwanseob is an associate professor in the Department of Biomedical Engineering at Ulsan National Institute of Science and Technology in Korea. He obtained his PhD degree in industrial engineering from North Carolina State University, and we're really excited to listen to Gwanseob's talk this evening, or this morning again, depending on where you may be. If you have questions, you're welcome to type them into the Q&A section of the chat down at the bottom of your screen, and I'll help moderate and facilitate some of that discussion as Gwanseob concludes. So with that, Gwanseob, we look forward to your presentation. Thank you for joining us and for giving this talk.
Thank you for the introduction. And you're also thanks for everyone for giving me this great opportunity to share my research, and also to introduce, to promote the event in 2024. I'm supposed to promote this event because I'm one of the organizing committee members. In 3 years, in 2024, we are hosting the 22nd Triennial Congress of IEA. It's going to be held in Jeju Island in Korea, which is the most beautiful area in Korea or in Asia, I believe. So we still have 2 years, but don't forget about this event, and keep in mind that we will actively promote this event in next year, and you will have more information about this event. Okay, let me start my main talk. My talk is about the smartphone. This is not a new anymore. It is our main interface between we and also the computers. We use this smartphone everywhere, every time. So we have to think about the potential hazards of intensive smartphone use. Mostly in previous research has focused on the smartphone use while seated or standing, but recently we were able to see a lot of occasions or some accidents and other concerns regarding the hazards of texting while walking on streets. So that's the main focus that I like to introduce today. Well, smartphone penetration rate, I don't have to mention this, but it's not that surprising. In fact, almost all adults or children are using their smartphones. They own their phones. It's not just users. We call this population. All entire population use their phones, and we heavily rely on the smartphones. We use this every day, more than 5 hours per day, based on recent statistics. In US, the adults use the smartphones over 160 times per day, and they use their phones more than 4 hours per day, and they touch or click or swipe their phones more than 2,600 times per day. And I believe these numbers would be a lot higher for young generations. Especially in Korea, our penetration rate is close to 100%. And some people have 2 phones, one phone for work, one for their personal life. And they use their phones every time, actually, while working or while they're commuting on subways or even on bed. So it's quite, the concerning fact that we are heavily rely on this interface. However, there are not much information or knowledge we have regarding the potential hazards on the cumulative exposures to these potential risks. What are the risks? First of all, when I'm using your smartphone, you are supposed to tilt your head down to look down the phone, because holding the phone in front requires your arms and shoulders to maintain this posture with this weight, about 200 grams of weight. And people typically feel discomfort or pain symptoms on the shoulder or arms first, and then neck. So typically they sacrifice their neck comfort for the arm comfort. So they put down the phones and they look down the phone, and they maintain the posture using their neck muscles. This is quite awkward posture. If they maintain these awkward non-neutral postures for hours, and if they are exposed to these awkward postures for days, weeks, or months, there must be some damages to those tissues, and there may be some negative effect on those musculoskeletal systems. And text neck syndrome is a simple word that refers to pain symptoms associated with intensive texting using their smartphones. The reason why we call this still syndrome is that we don't know exactly how these pain symptoms occur. So we don't have a clear picture of injury mechanism yet. Okay, let's think about the potential injury pathways between smartphone and pain symptoms. When we are using smartphones, yes, we tilt our head down to look down the phone, and we maintain this posture for a certain period of time. So to precisely assess those risk factors, we need to know how severe they maintain the posture, I mean, the amount of head tilt angle, and also we need to know the frequency of those exposures, and also duration of this head tilt down posture. And then we need to know what would be the potential consequences of these risk factors. Do we have higher muscular load compared to upright posture? We believe so, but we didn't have quantitative data before. Do we expect muscle fatigue? Do we expect pain symptoms? Or if it continues, do we expect temporary or permanent changes on our cervical spine tissues? We don't know. If these things happen, then what would be the consequences? Do we really, end up with this kind of, new generations? We don't know. So to answer those questions, I have conducted several research project studies since 2015. First of all, we wanted to know the posture exposure. Before that, there's no published records regarding the amount of head tilt angle when people are using smartphones. So we did a simple experiment in a laboratory. We created 20 young smartphone users, intensive users, students, and we measured the head tilt angle using motion capture system. We asked them to use their phones, in 3 apps, two-handed texting, one-handed web browsing, and one-handed video watching while seated, and also in standing. So there are two posture conditions and 3 app conditions. As you can easily, imagine, they maintain their head with more tilt angle when they're using their phones in seated posture. The angle was ranged around 40 to 45 degrees from upright neutral. And between those 3 apps, they tilted more when they were using their phones with both hands in texting. So text neck is a proper, expression about this concern. When they're using their phones in seated posture with both hands, they tilted more. They tilted the head more compared to when they're using other apps in other posture conditions. So in general, they maintained head tilt angle of 35 to 45 degrees downward when they're using their phones. And the amount of head tilt angle differed between applications. And then we had another question. Well, the previous study was conducted in a laboratory condition in a controlled environment. Then our next question was, would they behave similarly? I mean, if we collect these postures in their daily activities, would they really maintain 30 to 45 degrees when they're using their phones? So we did a kind of a field evaluation study. We attached wireless battery-powered the inertial measurement unit sensor, the orientation trackers, on a forehead of 31 students in our campus. And then we asked them to leave the lab and conduct their typical school activities, I mean, taking classes, go to library, and playing games with their phones. There's no restriction, but we continuously recorded the head tilting angle and the app usage records for 8 hours, typically from 9 a.m. to 5 p.m. Okay, let's take a look at the results. Among the 8-hour recording period, in average, they used their phones 2.5 hours. That time period includes the time period only when the phone was on, the screen was on. So it didn't include when they were listening to music. So it was quite surprising for me. I mean, they were supposed to take classes in our period. And during that 8-hour period, they used their phones more than 2 hours. And if you look at the distribution of time spent on each app, they used mostly email, texting, social networking, and web browsing. And those are the 3 most frequently used apps by our students. When they were using those apps, they maintained head down tilt posture between 30 to 35 degrees, which is somewhat similar to what we observed in our laboratory experiment in our previous study. And if you look at the bottom graph, it shows that they usually mostly maintain the head close to right or slightly downward when they're not using their phones. However, when they're using their phones, when they're watching their phones, they maintain their head approximately 30 to 40 degrees from right. So it confirmed our laboratory experiment, which means among 8 hours, they maintain this posture more than 2 hours. So that's quite intensive exposure to this awkward posture. Then we decide to measure their muscular load when they're using their phones, using the electromyography. So we put the EMG sensors on the posterior part of the neck to measure the EMG of neck extensor muscles in sitting posture, in standing, and also while walking, because walking is the most concerning the UCD scenario for us. So we recruited 21 young students. We asked them to use their phones in sitting, standing, walking, and conducting browsing with one hand and texting with 2 hands. If you look at the posture, it's similar to what we observed in our laboratory studies before. They tilted more when they're using their phones in seated posture compared to standing and walking. If you look at the standing and walking conditions only, the head posture was very similar. There's no significant differences. And however, if you look at neck muscular loads, and the numbers on y-axis, meaning the percentage relative to the activity while they are upright walking. So 250 for for the splenius muscle when they're browsing and while walking, meaning the activity of that muscle when they're conducting one-handed browsing while walking was 2.5 times greater compared to the activity of that muscle while upright walking. So if you look at the, if you compare the neck muscular load between standing and walking, and always it's greater for walking condition. However, the angle was similar between walking and standing. However, muscular load was a lot greater, a lot higher for walking condition. That's because of acceleration and deceleration while walking. Walking is dynamic motions. You know, when we walk, the head supposed to move up and down slightly. And we also measured the kinematics and postures. We were able to see that our participants were trying to maintain stable eye fixation on the phone by minimizing head perturbations while walking. And that effort requires more contraction of neck extensor muscles. That's because why the neck muscular load while walking was greater compared to standing, even with a similar head tilt angle. Next, we also was curious about the potential negative effect on low back muscles. You know, walking with a smartphone is a very awkward walking behavior. We look down the phone and we hold the phone with one or two hands. So there's no arm swing or limited arm swing and with head tilt down. So we're curious about what would happen if they walk with these awkward, non-neutral posture conditions. So we did another laboratory study with 20 young participants, students. We asked them to walk in 5 conditions: normal walking, and one-handed browsing while walking on treadmill, two-handed texting while walking on treadmill, and also we added 2 other, the conditions without smartphone, but limited arm swing. One arm bound and 2 arm bound conditions. So if you look at the results, these are the low back muscle, the EMG activity relative to maximum contraction capacity. So 6% means they use those muscles, the left second lumbar spine extensor muscles, use the 6% of each maximum contraction capacity when walking with the smartphone. Let's take a look at these columns. When they were using their phones while walking, the muscular load on their low back extensor muscles was approximately 50% more compared to when they simply walking without the phone or simply walking with arms bound, meaning the greater the muscular load on the low back is not because of bound arm conditions, it's because of a smartphone. They were holding their phone in front, they're maintaining head tilt down posture, and because of anteriorly shifted center of mass, we were able to see that they tried to tilt their upper body backward a little bit more to maintain the balance. And that effort requires more contraction of low back extensor muscles. And then that's the reason why we were able to see about 50% greater muscular load on the low back when they're using their phones while walking. So it simply, indicates the potential risk factors, risks of associated with texting while walking, not only on the neck, but also in the low back area. And the next question was, well, if they use these phones, for a prolonged period of time, then would muscle fatigue occur? Well, we assume yes, muscle fatigue would certainly occur. That's our assumption, but there's no reliable record. So we conducted a study. This is a recent study, not yet published. We are trying to publish. But in consequence, after 45 minutes of smartphone use in seated posture, we were not able to see the scientific, evidence of muscle fatigue. We were able to see the gradual increase of subjective discomfort ratings on neck. However, the objective evidence of muscle fatigue from the EMG sensors did not show the signs of muscle fatigue development, even after 45 minutes of intensive use. It means that the causes of it means that muscle fatigue may not be the main cause of their pain symptoms. There may be potential other causes of those pain symptoms. And we believe, we assume that maybe some changes on passive tissues because of head tilt down posture, neck flexion, may contribute to the occurrence of subjective discomfort. That's our goal for our future study. So this is a summary of what we found so far regarding musculoskeletal risk factors associated with the text neck. We were able to confirm that they maintain the head tilt down posture approximately 30 to 50 degrees. And they are exposed to those postures approximately 50% of their total smartphone usage period. And muscular load was 150 to 300% more on neck muscles and 50% more for low back muscles compared to upright walking. And there was a significant pain development. However, there was no or weak sign or indicators of muscle fatigue. So remaining question is, would the teeth change occur? And we have to look at it. And this is our current topic of our ongoing experiment. Well, if we find the answers for these questions, what should we do next? Do we have to simply let them, not to use their phones? We need to do some, make engineering controls, or we just wait until we adapt to this change? We don't know. We know the causes and we know the consequences, but we don't know how to control this. That's kind of a dilemma as an engineer, but we have to, at least let people know about this potential hazard. And next, the concern regarding texting while walking. It's not musculoskeletal hazard. It's more likely safety safety hazard because of distraction, pedestrian safety. In most previous studies have focused on the potential hazard associated collision with the vehicles. However, there are, accidents on walkway by pedestrians. So we conducted a laboratory studies to have better understanding of situational awareness of smartphone users while walking. We were, focused on the ground level visual cues, because when they were using their phones while walking, they look down, they don't look front. So they perceive visual signs or cues or warnings or potential hazard from their ground. So we need to know their perception ability about the visual cues on the ground. However, it was quite, it's not safe for us to do this in field study. So we studied in a laboratory using projectors and a treadmill. And we asked our participants to walk on the treadmill while using their phones. And then we projected visual cues in various locations on ground with the 4 by 6 dimensions. And then we measure their detection rate and reaction time after they perceive the cues. In 3 conditions: upright walking, browsing while walking, two-handed texting while walking. When they're walking upright, they detected pretty much all visual cues, regardless of their locations. However, when they're using their phones, they detected these closer cues, less than 80% of detection rate. And the closest cues detection rate was close to 60%, meaning they missed 4 out of 10 appearances. And also it means that to achieve more than 80% of detection rate, the visual cues should appear more than 2 meters in advance, which means they not perceive the cues properly if the cues appear within 2-meter area. So to confirm this finding, and also to study the potential effect of cue specification, we did another laboratory study with 40 young participants. At this time, we made a moving cue. We projected the cue from the further location, and we moved the cue towards the participants until the participant detected the cue. And we tried 3 different cue contrasts to figure out potential effects of visual contrast on detection rate, and also detection distance. So this is the result. And when they walk slower than they preferred, they detected the cues faster compared to when they're walking faster. That's quite understandable. However, if you compare the results between different cue contrasts, they detected low contrast cues they did not detect low contrast cues until the cues approached approximately 1.7 meters. Meaning, if a certain object hazard on the walkway has a low contrast, then smartphone users may not perceive those hazards until they approach approximately 1.7 meters. That 1.7 meters is remaining distance for them to properly perceive and take evasive actions, which may not be sufficient. So it confirms the results of a previous finding, and also it shows clear sign and evidence that smartphone users have approximately 2 meters before a collision with the potential hazard. If two smartphone users walking toward each other on the same walkway, same pathway, then 2 meters may not be sufficient for those 2 people to stop or take any evasive actions. They may collide, as you saw on this right side figure. So if you summarize, then we were able to see that low contrast cues resulted in slower detection. Faster walking also resulted in slower detection. In normal walking speed, in preferred walking conditions, people typically don't perceive hazards until they approach approximately 2 meters to the hazard. So 2 meters is a distance to collision. Now, well, this kind of result can be applied to the design of safety features on walkway or crossroads. You may be able to see some smart traffic signal near walkway, like the lightings on the entrance of walkway, but that is located just before the walkway entrance, and that's not sufficient may not be sufficient because smartphone users may not see this until they approach about 2 meters. And also this kind of obstacles should be clearly visible in advance for avoiding the collisions by the smartphone users. So we have to do some restrictions, and also we have to implement some engineering controls based on these kind of findings. Wow. I guess this is the last slide that I have prepared. So basically, the hazard of texting while walking include not only biomechanical stress on the cervical spine and lumbar spine, but also we have to think about walkway accidents because of distraction and reduce the situation awareness. Thank you.
Great. Thank you very much, Dr. Shin, for an excellent talk. Lots of exciting information there, and I'm sure there'll be lots of questions to follow up with. And also just take a moment to thank you for supporting the IEA and helping to bring forward the 2024 Congress in Jeju, South Korea. So looking forward to that as well. We do have a question coming from Nancy Black. Nancy.
Yes, I can see it.
Yeah, Nancy, I think I can unmute you if you'd like to unmute and just ask your question directly to Dr. Shin.
Can you hear me?
Yes, I can hear you.
Okay, so my question relates, you have that grill, that matrix there, and I was wondering to what extent lateral location affects the perception as opposed to where you are walking, so directly in front. Does that have an effect?
Yes, we did 2 studies. If you look at this, we had 3 lateral positions, about 1 meter distance between them. We are not able to see the potential lateral differences. There's some minor differences, but those differences were not statistically significant. They were able to, perceive those the cues in lateral positions pretty much in a similar detection distance. However, in this experiment, we were able to see some reduced detection performance for the lateral and the cues, but not that significant. So we didn't analyze the potential lateral position effects, but you are able to see some potential signs of a lateral position effect.
Thank you very much.
So if we map this, it's more likely like this. They missed most of far corners, far left, far right, and most distant cues. However, in closer distances, they were able to see all of those 6 cues with a similar detection range.
That's great. And if folks have other questions, you're welcome to raise your hand and we can allow you to ask your questions as well. Dr. Shin, you presented some work earlier on just before you transitioned into the texting while walking piece. And you spoke a little bit about the potential for tissue level changes. And I wondered how you've thought about kind of some of the viscoelastic nature of sustained holds and maybe getting into tissue creep as possibly implicated in the pain response. I wonder if you could speak to that a little bit for us. Yes,
that's our assumption. We actually did a study. It's not yet published. We asked participants to maintain this posture for 1 hour, not 45 minutes, 1 hour, some extreme conditions. And we actually made 3 different conditions. 1 hour normal smartphone use in this posture, and 1 hour without muscle activation, meaning they maintain its posture, but we support his head weight. And then another condition is 1 hour muscle-only condition, meaning they maintain its upright, but we pulled the head anteriorly. They were supposed to maintain this posture using similar muscle activity to this. We compared those 3 conditions. We were still analyzing, but we were able to confirm that there was no muscle fatigue. However, we were able to see some signs of viscoelastic changes of passive tissues. We were able to see the changes of flexion relaxation timing, And also we were able to see some signs of reflex activity of muscles, but it could be the muscle effect or it could be tissue effect. But we are still analyzing, but we see some signs of tissue change.
Interesting. That's very interesting. Any other questions from the audience for Dr. Shin today? Dr. Shin, seeing no other questions, we really appreciate you taking some time today to share with us your work. As we mentioned, for those, if you want to see this talk again, we will be posting it up on the IEA YouTube channel. Some really exciting work, and curious to see, Dr. Shin, how your work feeds forward into possible interventions to help prevent some of the potential risks, both from a pain perspective, but also from a safety perspective as well as you move forward. So please join me, everyone, again, in really thanking Dr. Shin for a wonderful talk this morning, this evening, wherever you may be in the world.
Thank you.